In this video, I want to talk about a matrix with an unknown in it, specifically the matrix I have up here. What I want to do is talk about what values of Q are going to produce a stable system, an unstable system, or a dynamically stable system. So the first thing I want to do is investigate the eigenvalues. Well, one of the things that we talk about in class is looking at the plot of the real eigenvalues. Now, in here, I wind up getting the eigenvalues look kind of complicated, but remember, they come from a characteristic polynomial of degree 2. So this is really the quadratic formula solving for lambda, the eigenvalues, in terms of Q. If I plot the real parts of this, you should notice that I get two very distinct portions of the graph. Kind of a straight line here, and it is a straight line, and these two tines sitting on the end. What I want to do is figure out different things about the norm, about the absolute value, the length of these eigenvalues. So the first thing I notice is that, well, this region right here, there's two distinct points that make up this straight line. Well, how is the straight line made up? Well, that means that I have an imaginary number. In other words, this quantity, this discriminant, the radicand, that has to be 0. So what I want to do is I want to solve for the discriminant being equal to 0. And if I do that, I wind up getting two numbers here. Now, what I'm going to do is put a comment here so I can remember these numbers if I decide to get rid of this. This is about 0.84, and this is 1.84, give or take, just so I can remember that. So I'm probably just going to comment that out so when I look at my solutions, I don't have a ton in there. So any Q value between these is going to produce a complex eigenvalue. Now, is it possible that I have a real eigenvalue equal to positive or negative 1? Well, what I want to do here, in order to visualize that, let me add two vertical pieces onto here. And I should notice, well, if you notice right around here, right around near 2, I intersect the graph in two places. And down here, I intersect in exactly 1. Now, I also notice that this blue curve here, the second eigenvalue that I am putting in here, this one right here, well, I'm not sure if that's actually getting hit. So I'm going to take that away for a second and see what happens. Well, it turns out that, well, it's hit up here, but not the other one. So I have the wrong one. Let me go put an eigenvalue, the first eigenvalue, and it looks like the first eigenvalue covers all the hits. So I want to focus on this. So after you notice that I have one value here that's complex, one value here that's real, and another value here that is real. So what I have here, if I look closely, I have my real eigenvalue. It's equal to 1. It's equal to negative 1. So I can easily solve for that. So let me solve for it right down here. I'll do an n solve. I'll take my first eigenvalue and I'll set it equal to 1. And I get about 1.9. And I think that corresponds to this number right here. So this one right here, I wind up getting a 1.9 for that answer. Now, what about the eigenvalue that's equal to negative 1? Well, let me try to estimate that really quickly. That looks at about here, negative, I don't know, 1.2, 1.3, something like that. Let me evaluate that. Negative 1.3, that's pretty good. So I'm just going to put that here so I can refer to it later. That's 2 out of my 3 points. Now, why do I want an eigenvalue of 1? Well, that's a stable system. Well, I got to make sure that it actually is a stable system when I look at the eigenvalue associated, well, when Q is 1.9 and I look at lambda 2. Don't forget about, you're dealing with two eigenvalues here. So let me go and put this other eigenvalue back here, the real part of it at least. Well, let's see what happens and let's see what I can get out of this here. I want to make this into a 2. Now, when I look at this, the orange one, well, the real value is bigger than 1. So that automatically means that the norm of the number, or the absolute value of the number, it's bigger than 1. So even though I have an eigenvalue that equals 1, its partner is bigger than 1. And I can actually show you that. So I'm going to take this 1.9 and I will put it into eigenvalue 2. So this is a nice way to do this. I'm going to take eigenvalue 2 and I will do a forward slash period. Then the variable here is Q, and I want to put in this 1.9. So this should substitute in a 1.9 in for Q. Let me hide some of this stuff because I already know outputs for a lot of this. And the thing is, I wind up getting a 1.4 out of this. So if I look at this area and I plug in that 1.9, one of my eigenvalues is 1, but the other one is 1.4. So when lambda 1 is 1, that actually tells me that lambda 2, well, that's actually equal to 1.4. This is not a stable system anymore. I have to make sure both eigenvalues are appropriate for this. Now, what about this negative 1.3 here? Well, let me do the same thing over here. Let me take this, I'll copy it down here, and let's put in a negative 1.3. Well, I notice, actually, let me hide this. I notice that I get a 0.2. So for this one tells me that my lambda 2 turns out to be 0.2. And I know that high powers of that, or powers of that, are going to tend to 0. So this tells me that I have a, well, not a stable system, but a dynamically stable. A dynamically stable system. How come it's not stable? Well, negative 1 to a power is going to oscillate between negative 1 and 1. This one right here, I never put in here, it's unstable. It actually goes off to infinity in these things. They become these the vectors that we produce using the chain through in the recursive definition, I couldn't remember that for a second, they grow without bound. Now, there's something else that's going on here. Well, I talked about eigenvalues being 1, eigenvalues being negative 1, but this point right here, I know it's going to be unstable. And I know it's unstable because the real part is 1. That means, well, it is complex. So the imaginary part is going to push it above 1. But what about eigenvalues that are complex, that have a norm of 1? Now, there's many ways to do this. But what I want you to notice that if I have values, and I will bring this up here, if I have values, Q values between here, then I produce complex eigenvalues. So let's just for a moment, I assume that I have a complex eigenvalue. Well, that means this part right here, the stuff I have highlighted, that produces the I, the square root of negative 1 part. So the stuff I have highlighted, this part, oh, and don't forget about the 1 over 20, you can easily miss that. This part right here with the 1 over 20, that's my imaginary part of all of this. So let me give you another definition here. Let's say the imaginary part is really, let's see, let me get a fraction, 1 over 20 times that object right here. Now I want to be really careful about what I just pasted there. I'll come back to why I need to be careful. Now the real part of this, well, that's the stuff that's not the imaginary part. I don't even know how to say that without kind of giggling. So I'll have this, and I have a real and imaginary. Now, notice that I said a real and imaginary. So I want to be really careful here. Let me just write a few things down, and then we'll come back to this. So, if I have a complex number, and I want to look at the norm of this thing, well, that's equal to the square root of a squared plus b squared. That's the definition of the norm of a complex number. Now, what I have over here, I have this real part and this imaginary part. That's what I had in my Mathematica file. And I literally mean the imaginary part. I mean I have the whole BI sitting there. So what I can do is I can modify this a little bit. And I want you to notice something. That if I took BI, like the whole imaginary part, and I squared it, well, what do I wind up getting? I get b squared and I squared. Well, I squared is -1, and so I get negative b squared out of this thing. So what I can do is I can redefine, not a plus sign here, but a minus sign, is I can rewrite it like this. So that means my real and imaginary piece, when I want to figure out the norm of my numbers, I'm really going to look at the square root of that real piece minus the square of the imaginary piece. And I want this to be equal to 1. That's my goal out of all this. So here we go. I'm going to head back to Mathematica really quickly. And let's see if I can actually type this in. I want to end solve. I want the real piece squared minus the imaginary piece squared. And you can call these anything you want. I just called it RE and IM. And notice that I have lowercase letters here. And I want that to be equal to 1. So let's see. If I do my output here, I wind up getting a Q of 1.1. Now, let's see if I can do a little investigation here. So when the real part is when Q is 1.1, what do I actually get for my eigenvalues? Well, let me go back and I'm going to copy this. And I'm going to pull this into a new cell. But what I would like to do is I'm going to set Q equal to 1.1. And if I do that, I wind up getting 2 eigenvalues. Now these eigenvalues here, what can you tell me about the norm of these things? Well, I'm not even going to type this out. 0.8 squared, 0.64. 0.6 squared, 0.36. 64 plus 36 is 1. Well, 0.64 is 1. So I get norms of 1. And notice that these come in conjugate pairs. You know, the plus or minus square root part, you'll see that right here. So when Q is equal to 1, my eigenvalues have the correct norm. Now I also said that if I had negative 1.3, if I can actually type this in correctly, I wind up getting 2 eigenvalues. Well, the norms aren't 1. The norm for this one is 1, but this one is just 0.2. When I'm looking at powers of this, the 0.2 collapses to 0, or the limiting value is 0, but the negative 1 is going to oscillate back and forth. Now, the other number that we had, I believe, was 1.9. Now, that was actually a very intriguing number here. I get an eigenvalue of 1 out of this, but I also get an eigenvalue of 1.4. 1.4 powers of that go to infinity. They're unbounded. So I do not get any limiting factors here. They don't stabilize. So I come back, I'll go back to the top here and let's summarize this really quickly. When Q is equal to 1 point, whoa, I got rid of the 1. And Q is equal to 1.9, it turns out that lambda 2 is 1.4 and I get an unstable situation. When Q happens to be negative 1.3, well, lambda 1 is negative 1 and lambda 2 is small. It goes to 0. So I get a dynamically stable. I spelled dynamically wrong. Dynamically stable system. Now I have some more investigation to do. When I look at my values of Q between these, and you'll notice that I didn't get anything between, and I was looking at a picture the whole time to make sure that I'm doing this correctly. I was looking at this picture right here. This value that I got here, where Q is equal to 1.1, well, I looked at an imaginary part, and I had to remember it was really an I involved in there. So I squared was negative 1. That's going to compensate with this minus sign and make it a plus eventually. Well, I wound up getting 1.1. Now, when Q is 1.1, I went over here and I said, well, take a look at the two eigenvalues for this, and both of them had modulus 1. And that's how I wind up getting a dynamically stable system. So there was a lot of investigation here, and there was a lot of, let's see what's going on with the picture. Now, there are other ways to do this, but this gets down to the heart of imaginary and real parts of numbers and breaking apart things that look like this into its real and imaginary components and then dealing with it. I hope you found this video helpful. If you have any questions, just let me know. Have a great day. See you later.